Have you ever wondered how we actually know the things we study in science? I mean, we have all learned in school that the earth weighs around 5.97 into 10 raised to 24 kilograms, that its radius about 6,371 kilometers, and that the moon is about 3,84,000 kilometers away from us, and that the charge of an electron is around minus 1.6 in 10 raised to minus 19 coulombs. We even know that the distance between galaxies that are billions of light years away. But have you ever stopped and asked yourself, how do we even know all this? How did the humans figure out the weight of the earth or distance to a star we can barely see? These aren't just numbers, these are discoveries. And today, I want to take you on a journey behind those numbers to explore how we actually measure the universe around us, from the tiniest particle to the vast stretches of cosmic space. So get ready, because this is not your regular science class. This is about the untold detective story of science, how we discovered the world, one experiment at a time. Let us start more than 2000 years ago with a man named Eratosthenes, a Greek scholar living in Egypt. He made an observation that changed how we see the world forever. Eratosthenes noticed that at noon during the summer solstice in the city of Syene, modern day in Aswan, the sun was directly overhead. You could see the reflection of the sun at the bottom of a deep well. But at the same time in Alexandria, which is north of Syene, vertical sticks cast shadows. That told him the sun wasn't directly over the head. Using just a stick, a shadow, basic geometry, and a bit of walking distance, he calculated the circumference of Earth. He measured that the angle of the shadow in Alexandria about 7.2 degrees and used the distance between Alexandria and Syene, which is estimated to be around 800 kilometers. So 7 degrees is 1 by 15th of a circle. Multiply by 800 kilometer by 50 and you get 40,000 kilometers. That is remarkably close to the modern value of Earth's circumference. No satellites, no GPS, just pure logic and observation. Fast forward to the 18th century. A scientist named Henry Cavendish carried out one of the most delicate experiments in history. His goal, to weigh the Earth. Now obviously he didn't put Earth on a giant scale. Instead he used what is known as torsion balance. Picture this. Two small lead balls attached to a rod, suspended by a very thin wire. Nearby, he placed two large lead spheres. Gravity caused the small balls to be attracted to the large ones, and the rod twisted slightly. By measuring the twist and knowing the mass of the balls and the distance between them, Cavendish could calculate the gravitational constant G. Once G was known, we could plug that into Newton's law of universal gravitation and work backwards to find the mass of the Earth. The genius of Cavendish wasn't just in measuring gravity. It was in realizing that this would allow us to find the mass of something we couldn't directly weigh. The moon feels close, right? But how do we know it's about 3,84,000 kilometers away? There are several ways we have measured it. One of the earliest methods was parallax. Astronomers observed the moon from two distant locations on Earth at the same time and measured the slight differences in its position against the background stars. But the most accurate method today? Laser ranging. During the Apollo missions, astronauts placed retroreflectors, basically mirrors, on the moon. Scientists here on Earth shoot lasers at those reflectors. The laser beam bounces back, and we measure the time it took for the round trip. Since we know the speed of light, we can easily calculate the distance. This method is so precise that we can detect changes in the Earth's distance just a few centimeters. Now let's go further. How do we measure the distance to planets like Venus or Mars, or even to the Sun? For nearby planets, radar is the most effective tool. We send a radio wave towards the planet and measure how long it takes to bounce back. This is exactly like echolocation but on a cosmic scale. The distance to the Sun was famously calculated using the transit of Venus. When Venus passes directly between Earth and Sun, Observers from different points on Earth can measure the slight difference in its path. With geometry, that difference helps us determine the distance between Earth and Sun, called the astronomical unit. Stars are far away, so far that radar doesn't work. Here we rely on stellar parallax. We take a picture of a star from Earth in January and another in July, 6 months later. When Earth is on the opposite side of its orbit, the nearby star appears to shift slightly compared to distant background stars. That tiny shift, measured in arc seconds, helps us triangulate the distance. This works well for stars within a few hundred light years. For stars beyond that, we use standard candles, special type of stars like Cepheid variables. These stars pulse in a predictable way, and their brightness tells us their true luminosity. Comparing that with how bright they appear, let us find the distance. Now we are zooming out to entire galaxies. When Edwin Hubble observed galaxies, he noticed that the farther away a galaxy is, the faster it seems to be moving away from us. This is redshift. Light stretched into longer wavelengths as a galaxy moves away. By measuring how much a galaxy's light is redshifted and using Hubble's constant, we can estimate its distance. That's how we know some galaxies are billions of light years away. Let us switch scales. We are going to microscopic. How do we know that the charge of an electron is minus 1.6 in 10 raised to minus 19 coulomb? In 1909, Robert Millikan performed the famous oil drop experiment. He spread tiny oil droplets between two metal plates and applied a voltage. Some of the droplets were charged. By adjusting the voltage, he could make a droplet hover in midair, meaning the electric force was exactly balancing the gravity. By analyzing the forces and knowing the mass of the droplet, Millikan calculated the charge on a single electron. That's how we arrived at the value minus 1.6 in 10 raised to minus 19 coulombs. When we talk about the size of atoms, we are in the range of nanometers and angstroms. But how do we measure something so small? One method is X-ray diffraction. When X-ray hits a crystal, they scatter in a predictable way. The angles and density of these scattered rays give us information about the arrangement of atoms inside the crystal. Another modern method is scanning tunneling microscopy. It uses a sharp tip that moves across the surface just a few atoms away. Electrons tunnel across the gap, and that current is measured to build a 3D image of the surface, atom by atom. Many of the constants you hear about, Planck's constant, Boltzmann constant, the speed of light, are known through incredibly clever experiments. For example, Planck's constant was determined by studying black body radiation and photoelectric effect data. The speed of light was measured by Fizeau and later Foucault by using rotating mirrors and light beams reflected over long distances. We used to define a second based on the rotation of Earth, but today time is measured using atomic clocks. Cesium atoms oscillate at a precise frequency when energized. 1 second is defined as a specific number of these exact oscillations. These clocks are so accurate they won't lose a second for millions of years. So the next time you read a number in a science textbook, don't just memorize it, wonder about it. Every digit is the result of someone's creativity, patience and perseverance. Whether it's a stick casting a shadow in ancient Egypt or laser bouncing off the moon, we have built our understanding of the universe through observations, experimentation and imagination. This is the beauty of science. It's not just what we know, it's how we came to know. And now you know too. Thank you for watching.